So we're now going to talk about the second differential or the second derivative, what you get when you differentiate again, so two lots of differentiation of the original function. So this whole page here is about diagnosing whether a turning point is going to be a maximum, a minimum, or something called a point of inflection. Everything we talk about on this page here is talking about turning points, positions where the gradient is zero. So that's a given for everything else I'm about to say now. So in this example here, we have something which is going downwards, it's decreasing with a negative gradient. It pauses briefly at the bottom, it has a zero gradient, and then it begins to increase. It's an increasing function over this part. Okay, but at this particular point here, it is a stationary point or a turning point. If we look at this one here, this one is increasing, it's going up and up and up and up and up, and then it reaches this point here where it briefly pauses. That's a turning point or a stationary point, and then it begins to decrease. These turning points are happening when we're changing from a negative to a positive gradient or a positive to a negative gradient. Now, below here are two other examples of when you can get one of those stationary points. These positions here are stationary points or turning points. At that particular point there, this thing is not going up and it's not going down, so it's definitely a stationary point. If you plugged a value of x into dy dx, you would get 0 here. But look at what's happening. It was increasing, increasing, increasing. It was slowing down a bit as it was increasing. It paused briefly. It had a 0 gradient. It rested, so to speak, and then it began to increase again. Rather than changing like these ones did from going down to going up or going up to going down, this one is always pretty much going up. It just pauses on the way. For this one here, it's going down, 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 slows down a bit, it pauses briefly, it's not going down anymore at that position, and it's not going up either, and then it continues to go downwards. This here is called a point of inflection. So, if you found out that dy dx is 0, you might be talking about a minimum, you might be talking about a maximum, or you might be talking about a point of inflection. We use the second differential to diagnose between these. If you worked out that dy dx is 0, and you then plug your x value into d squared y dx squared, okay? If you get a value bigger than 0, you're talking about a minimum. If you get a value of d squared y dx squared which is less than 0, you're talking about a maximum. And if d squared y dx squared is 0, you don't really know anything at all, okay? Now, this is maybe slightly misleading, but it's clarified underneath. If d squared y dx squared is 0, it might actually still be a maximum, it might actually still be a minimum, or it could be a point of inflection. So, we've got to think very carefully here. If you get the second derivative being greater than 0, it is categorically a minimum. Okay? There's actually other ways a minimum can happen. Sometimes this can give you a minimum. But if this is true, it is definitely a minimum. If d squared y dx squared is less than 0, it is a maximum. There are other ways that could happen that you get a maximum down here, but this one here definitely means it's a maximum. If you get this thing here, then all bets are off. You know nothing. It could be a maximum, it could be a minimum. Okay? It could also be a point of inflection. So why this statement is here is because if d squared y dx squared is 0, that's the only time you're going to get a point of inflection. Using some fancy kind of words, if I talk about a point of inflection, if you have a point of inflection, then that means for definite that the second derivative is 0. But that does not go the other way. It's not true that if d squared y dx squared is 0 that you're talking about a point of inflection. If d squared y dx squared is 0, you could be talking about a maximum, a minimum, or a point of inflection. We'll investigate that more in a second. So, one more time, you can't say it enough. If dy dx is 0, then you have a turning point. How will you find out what kind of turning point? Well, you differentiate again and you plug in the value of x at that turning point. If you get a value bigger than 0, great. You know for a fact it's a minimum. If you get that d squared y dx squared is less than 0, brilliant. You know for a fact it's a maximum. If you get that d squared y dx squared is 0, bang on 0 itself, then it's the only time you're going to be able to get a point of inflection, but it might actually still be a maximum minimum. This one opens a whole can of worms. Now, very briefly, because it is important to understand these things, it goes slightly against expectations, perhaps, that d squared y dx squared being greater than 0 is a minimum. The word greater than and minimum doesn't seem to make much sense. Here, again, it's sort of against people's expectations that d squared y dx squared would be less than 0 for a maximum. And the reason for this is, these two turning points here, you can see the graph in that region is very different. Here, the shape of this thing here mirrors the shape of what we call a convex graph earlier. This was the condition I mentioned earlier for a convex graph. They're fundamentally graphs which are sort of doing this kind of shape. So that's decreasing, that's increasing, but they've got that kind of convex shape. So this actually comes from the principle of convexity. This one here comes from concavity. You do not need to know the words convex and concave, but it maybe reassures you slightly that there is a reason for this being against what you would expect. So in an exam, if you get a turning point, if you get dy dx is 0, you found a stationary point, you found a turning point. If you then use d squared by dx squared to diagnose it, get a value bigger than 0, you've got a minimum. If you get it less than 0, you've got a maximum. If you get it equal to 0, you have to do some more investigation. So let's have a look at what we're going to do if that's the case. If you get that d squared by dx squared is 0, you are going to have to investigate which of these it is. Now, this is not going to give you the answer, okay? This is not telling you. So what we do is we sort of go back to thinking about it, and we sort of say, well, let's look at the gradient either side of that point. Now, either side of that point is a very, very loaded word mathematically, okay? How close are we talking about? Well, we'll go into detail on that in a second. So, if I've found a point and I do not know whether it's a maximum minimum of point inflection, I will investigate what the gradient is before and what the gradient is afterwards. Okay? In this case here, if I plug in a value just before and get a gradient which is positive, that means it's going up. If I plug in a value afterwards and get a gradient which is positive again, then it must be a point of inflection. Maximums and minimums don't do that. You don't get a positive gradient before and after a maximum or a minimum. That means it's a point of inflection. Similarly, if you plug in a value just before and get a negative gradient, then a negative gradient when you plug a point just afterwards, then you're talking about a point of inflection as well. If you've got this kind of condition here and you plug in a value just before and get a positive gradient, you plug in a value just after and get a negative gradient, then you're talking about a maximum. And finally, for completeness sake, if you plug in a value just before and get a negative gradient, and then plug a value just afterwards and get a positive gradient, then you're talking about a minimum. That's sort of the fundamental definition of these points. Anticipating a problem you might have here, you are plugging in to the expression for dy dx either side. You're interested in whether it's going up or going down. You're not plugging into the value of y. Okay? So you're plugging in to find out whether it's going up or down either side, not what the value of y is. So if you get d squared by dx squared is 0, you will pick points either side of the stationary point and you will investigate the gradient. Okay? If you get negative before or positive afterwards, it's a minimum. If you get positive before and negative afterwards, it's a maximum. If you get positive before and afterwards, or negative before and afterwards, it's a point of inflection. So before we go any further, I said you have to go either side of it. Now you have to stay close, but obviously you don't want to go too close. This is a C1 exam, and if you start going for values like 0.0001 away from it, it's going to be very difficult to work with. So how close is close enough? Well, as long as you don't go beyond the next turning point. So let me draw you a little diagram. So if I was investigating this particular graph here, so if I was investigating this and I'd sort of found out that I had a turning point here. Now, clearly we can see in this case that it's a maximum, but if I plug in some points, and I'm trying to work out which values to plug in, if I plug in here and here, that's fine, okay? You could even go for here and here, okay? Or there and there. Those are all fine. You couldn't, though, go for this value and this value, okay? And the reason is that this value here has gone too far away, okay? This one here is fine, okay? But this one here is too far away. This would suggest this is a point of inflection because here this has got a positive gradient, here this has got a positive gradient. And the reason is that you're not really investigating this turning point, you're sort of investigating the combination of these two. So, again, if I was investigating this turning point down here, I could try those two values, or I could try those two values, or I could try those two values. I couldn't try that value and that value. So when you're testing values either side, you can't go further than the adjacent turning points, if there are any.